something changed. On October 29th, 2025, as the interstellar traveler known as 3, I-Atlas reached its closest point to the Sun, its perihelion. It did something no one expected. For a few hours, its light flared so sharply that even automated solar observatories momentarily froze. And from that moment on, everything astronomers thought they understood about this object began to unravel. It wasn't supposed to happen this way. The models predicted a slow brightening, a gentle rise in activity as solar heat vaporized its icy shell. But instead, Atlas detonated a surge in brightness that doubled within a single solar rotation. It was as if something inside had awakened. And here's the part that makes scientists uneasy. This isn't a comet from our own solar system. It's an interstellar object, a wanderer that may have traveled for billions of years through the dark gulf between stars. It has seen more suns than we can name, endured more radiation than any spacecraft we've ever built. Yet it arrived here, intact, until now. As its orbit tightened, a strange pulse appeared in the data, a rhythm in its light curve, almost like a heartbeat echoing through the void. At first, astronomers thought it was noise, but the pattern persisted, repeating every 17 minutes. That's when the word explosion started appearing in the reports. No one could explain why. The heat alone couldn't do this. The chemistry couldn't do this. Even NASA's early briefings quietly replaced the phrase outburst event with energetic anomaly. Because if this was just a comet, it was breaking every rule we know. Something changed, and no one knows what. The first clue came not from a telescope image, but from a spectrum, a thin band of light stretched into its hidden code. When scientists compared Atlas's spectrum with that of the Sun, they saw something that shouldn't exist. The light wasn't golden or white like ordinary solar reflections. It was blue, bluer than the Sun itself. That shift toward blue wasn't just aesthetic, it was chemical. Inside that glow, spectrometers picked up the fingerprints of diatomic carbon C2 and amidogen NH2. Those molecules form only when frozen ices suddenly leap into gas, skipping the liquid stage entirely, a process called sublimation. And that's where the story turned explosive. In the 2 weeks before perihelion, instruments recorded that 3I Atlas was losing roughly 5.7 times 10 to the 28th power water molecules every second, about 40 times more than it was just a month earlier. 40 times more water pouring into space. Every heartbeat of the Sun. One scientist described it simply a fire hose in full blast. Imagine a mountain of ice turning to vapor faster than an industrial jet engine could breathe. The Sun wasn't melting Atlas. Atlas was venting itself. That blue glow. Those molecular fingerprints. The impossible rate of outgassing. They're not just data points. They're a message, written in light. Because that blue isn't a color, it's language. But if so much ice was bursting into vapor, one thing should have been blazing across the sky a dust tail. So why don't we see it? When the images came back from the solar coronagraph SOHO. Stereo. And goes. 1-9 astronomers expected to see a classic sight. A blazing dust tail arcing away from the Sun. That's Comet Physics 101. But when the frames were aligned and enhanced, the shape that appeared on the monitors made no sense. There was no tail, no broad, dusty plume scattering sunlight into space. Only a stretched, featureless glow, faint, elongated, and strangely clean, like a torch beam blurred by mist. The data confirmed what the eye saw: plenty of gas, plenty of vapor, but almost no solid dust. And that shouldn't happen. When ice sublimates, turning straight from solid to gas, it normally drags tiny grains of rock and metal with it, creating the glowing tail we see behind comets. So what happened to Atlas's dust? Where did it go? Two explanations are on the table. The first, maybe this object was born dust poor, formed in a stellar nursery where solid grains were rare, leaving it mostly ice and gas. The second, the dust is there, but the solar wind, a river of charged plasma, has stripped or scattered it before it could form a coherent tail. Either way, what we're seeing breaks the rules of how comets behave under solar radiation. A comet without a dust tail that's like a dragon breathing, vapor without smoke. But maybe the answer isn't floating in space at all. Maybe it's buried beneath the surface inside a shell time itself has forged for billions of years. 3. Atlas has been drifting through the interstellar deep, a place without sunlight, without warmth, and without protection. Out there, the only constant is radiation, a relentless storm of galactic cosmic rays slamming into its surface, particle by particle, century after century. Those impacts didn't destroy the comet. They reshaped it. Each high-energy collision broke chemical bonds, rearranged molecules, and slowly cooked the upper layers into something entirely new, a hardened crust of irradiated material. Computer models from the Royal Belgian Institute for Space Astronomy suggest that this crust could reach between 15 and 20 meters deep, thick enough to seal away whatever pristine ice once lay beneath it. That means the surface we see isn't the true face of Atlas at all. It's a mask, sculpted by radiation, toughened by time, hiding a much older heart below. In behavior, this crust acts like armor, insulating the inner ices, keeping them stable, even as the comet passes through regions of increasing solar heat. But once that armor breaks, once a crack opens deep enough for sunlight to reach the hidden layers, the result is explosive. The journey itself has forged its protection. Time is both the enemy and the engineer. Atlas wears its past like armor. But if there's armor, then something or some condition must have pierced it right at perihelion. What kind of force can break through 20 meters of cosmic crust with a chill, not heat? One of the leading natural models trying to explain Atlas's outburst is known among astronomers as the carbon dioxide cooling layer hypothesis. It suggests that long before the comet reached the inner solar system, it had already begun to release carbon dioxide CO2 gas from shallow pockets beneath its surface. That slow leak acted like a refrigerator, cooling the outer crust instead of heating it. In other words, CO2, escaping at a distance of several astronomical units, created what scientists call a cold jacket, a thin insulating shell that kept the underlying water H2O ice frozen solid, even as the comet drifted closer to the sun. But every system has a breaking point. As Atlas approached perihelion, the CO2 reserves thinned, and the protective cooling vanished. Within hours, sunlight struck the freshly exposed ice, and the reaction was instantaneous. The water turned directly to vapor. Pressure built up beneath the crust, and the comet's brightness doubled almost overnight. It's a simple, elegant chain reaction. The sun doesn't ignite the comet, it merely removes the safety lock. A thin layer of carbon dioxide delayed the blast until nothing was left to shield it. This theory fits the timing perfectly, the sudden brightening right at perihelion. When the cold jacket failed, but even if it explains the flash, it doesn't explain the pattern or the path, because Atlas's orbit and its mass tell a much larger story. What kind of comet moves in a line so straight, with a mass so enormous, and behaves like something designed rather than born for decades? Planetary scientists have struggled with a paradox. How do worlds begin? Computer models show that when dust grains in a young star's disk grow to about a meter in size, they stop sticking together. Instead of forming planets, they collide and shatter. This is known as the meter-size barrier. So how does the universe leap over that barrier? One bold theory proposed by astrophysicist Suzanne Falsner and her team suggests that interstellar objects like Atlas might be the missing ingredient. They call them planet seeds. Imagine a newborn star surrounded by a swirling disk of gas and dust. Now picture an interstellar traveler drifting through that chaos already, hundreds of meters wide, dense enough to pull in surrounding material by gravity, alone. That seed becomes the nucleus, around which a new planet begins to grow. That single idea could solve one of planetary science's oldest mysteries, how to bridge the gap between dust and worlds. And it makes Atlas far more than a comet. It makes it a survivor from a time when other stars were building their own planets. Based on early estimates, Atlas could weigh around 33 billion tons, making it even heavier than Halley's Comet. That kind of mass would make it a perfect planet seed candidate, large enough to attract matter, but small enough to survive ejection from its home system. In that sense, Atlas isn't just passing through our solar system, it might be carrying with it the DNA of forgotten worlds, the blueprints of planets that never got the chance to form. Sometimes, the universe doesn't build from dust. It builds from seeds that wander between the stars. But how do we know if Atlas is just a strange natural relic or something fundamentally different in nature? To find out, we need a test, a way to tell the difference. Science moves forward by asking hard questions and then trying to break its own answers. So, if we want to know whether Atlas is a natural object or something else entirely, we need a checklist, a series of tests that can be falsified, not just believed. Test 1. The thermal trigger. If Atlas's activity turns on or off at precise distances from the Sun at specific thresholds, rather than following a smooth curve tied to temperature, that could suggest an internal, non-thermal mechanism. In plain terms, if it behaves like a switch instead of a melting snowball, that's a red flag. Test 2. The microtrajectory. Normally, the jets of gas that escape from sublimating ice act like tiny thrusters, nudging the comet's orbit in predictable ways. But if the direction or magnitude of those pushes doesn't match what we observe, if the math breaks, something else might be steering it. Test 3. The radio signature. A natural plasma emits random static across broad frequencies. But a modulated signal, a pattern that repeats or encodes, would hint at something structured. That's why scientists will keep listening in radio bands while Atlas recedes from the Sun. Test 4. The geometry. Most comets are chaotic, irregular shapes, asymmetrical jets, random outbursts. But if Atlas shows unusual symmetry in its jets or core structure, That could indicate internal design either by physics we don't yet understand, or by intention. In science, a good hypothesis isn't the one that convinces you, it's the one that survives every attempt to kill it. The real test begins now in the post-Perihelion phase, when Atlas's armor could crack and reveal whatever lies within its core. As 3, I-Atlas moves away from the sun. We're entering what astronomers call the golden observation window, the brief period when the comet becomes visible again from Earth, between mid-November and late December 2025. During this time, every telescope from amateur backyard scopes to NASA's Swift UV telescope will be watching for one thing: how Atlas behaves now that its armor has cracked. To track this, we're setting up 3 key observation KPI scenarios. Think of them as 3 possible storylines, and we'll be monitoring them in real time. Scenario A, the textbook fade. Atlas dims gradually as solar energy drops. The sublimation slows. The jets fade, and the comet quietly drifts back into darkness. That's what the models expect. Scenario B, the pulse. The brightness wavers up and down as new material emerges from beneath the cracked crust. This would mean Atlas is exposing fresh layers of volatile compounds such as water, H2O, hydroxyl OH, or even carbon dioxide CO2. Scenario C, the phase shift. The comet's activity no longer matches its distance from the sun. It brightens or dims at the wrong times, behaving like it's responding to thresholds rather than heat. That's when we'll know something unusual is happening inside. Every week through December, new data points will update this dashboard, a live graph of brightness, activity, and spectral composition. And if one of these curves deviates from the expected line, you'll see it here first. Because we don't wait for rumors, we measure. But no matter which scenario wins, one question still hangs over the entire mission: where is the full dataset? Every interstellar visitor is a once-in-a-lifetime opportunity, a window that opens for a few short weeks, then closes forever. Once Atlas fades beyond our reach, there won't be a second chance. The data we collect right now will define how humanity remembers this object for generations. That's why data transparency matters more than ever. Professor Avi Loeb has already called on NASA to release all raw measurements, light curves, spectra, radio readings for open global analysis. Because when an object from beyond the stars passes through our neighborhood, that data belongs to everyone. Our channel is doing the same. We've built a public tracking dashboard, updated weekly with the latest photometric data and brightness indices from observatories around the world, including amateur astronomers who submit their own verified readings. You'll find links in the description to cross-check every figure we cite. Follow the data, not the drama. Because when it comes to interstellar science, belief means nothing. Measurement means everything. The truth is, we still don't know whether Atlas is just an extraordinary natural comet or something else entirely. But the answer won't come from speculation. It will come from the evidence. The universe has spoken. The question is, are we listening carefully enough in the next chapter? We'll decode 3 of the most sensitive indicators: the activity lag versus temperature, the OH spectral pattern, and the jet morphology map clues that could completely change the story of Atlas. If you want to be the first to see what the data reveals, hit subscribe, turn on notifications, and join us as we follow this cosmic mystery unfolding in real time. Top of form. Bottom of form.